Welcome again. So our first problem is to evaluate the integral 0 to 2 pi d theta over 5 minus 3 cosine theta. So this is a problem on application of contour integration to integrals within a unit circle. So to evaluate such integrals, you have to convert the integral from theta to the variable z, and then apply the Cauchy residue theorem to work out the solution for the contour integral. So solution. So we'll say we know that z is given by e raised power I theta on a unit circle. Then dz is the same as I e raised power I theta d theta, which means the theta is dz over I e raised power I theta, which is the same as dz over I times z, because the value of e raised power I theta is z. And then also cosine of theta is given by 1 over 2 e raised power I theta minus e raised plus e raised power minus I theta. So which is the same thing as saying 1 over 2 into z plus z raised power negative 1. So it's the same as a half into z plus 1 over z. So we are going to use these values to substitute into the integral 0 to 2 pi of, so this implies that integral from 0 to 2 pi of d theta over 1 of 5 minus 3 cosine of theta will be the integral now along, so this is 0 to 2 pi. Now I can say d theta 5 minus 3, where there's cosine of theta, we put e raised power theta I plus e raised power theta I minus theta I divided by 2. So which is the same thing as saying integral from 0 to 2 pi of the theta over, so you see, okay, you can have this as 5 and then minus 3 into 2 and then e raised power theta I plus e raised power minus theta I. So which means we'll have the integral 0 to 2 pi. Now you have the theta over 5 minus 3 over 2 e raised power theta I plus e raised power minus theta I. If we multiply numerator and denominator by 2, I will not have changed the equation. So I'll have the integral from 0 to 2 pi. So this will be 2 theta. And then, so 2 times this will give me 10. 2 by this I'll get now minus 3 into e raised power I theta plus e raised power minus I theta. So now this integral now changes to the contour integrals along C. So I'll have 2, 10, and then minus 3. Where there's e raised power theta, I put z. Where there's this one, I put 1 over z. And then the theta is the same as the z over iz. And then you specify that C is a unit circle. So once you change from theta to the variable z, then it changes now from having limit 0 to 2 pi, but then is integral along C. So this will be the integral along C. Let's say 2 dz. Now here I have 10 minus, if I factor out z, I'll have 3 over z, and then z squared plus 1. Then I have I z here. So this is the same thing as this multiplied by every term here. I have integral along C 2 dz over iz times this will get 10 iz, then minus z cross with z, so I'll have 3i into z squared plus 1. So because I have an I on this term and an I on this term, I can factor it out. So I write 1 over I integral 2 dz over, this will be 10z minus 3z squared minus 3. So which I can write as 1 over I along C. Now, because these are quadratic, so I can factor out negative sign. So I write negative, and then 2 over 3z squared minus 10z plus 3 dz. So this is what we have. So then now, here, I can also factor out 2. So I write this one negative 2 over I integral of dz over 3z squared minus 10z plus 3 as my integral. So we concentrate on the value of this integral. Now, once we get the value of this integral, we just multiply by minus 2i, we get the answer. So let me call this one star. So if I have this integral I dz over 3z squared and then minus 10z plus 3. So here, f of z is given by 1 over 3z squared minus 10z plus 3. So then I have to get the poles of f of z. Poles are given by taking 3z squared minus 10z plus 3 equal to 0. And then this quadratic will have product is 9, sum is minus 10. So numbers minus 1 minus 9. So I have 3z squared minus z minus 9z plus 3 equals to 0. So doing the pairing, I'll get z into 3z minus 1 minus 3 into 3z minus 1 equals to 0. So z minus 3z minus 1 is 0. So which implies z equals to 3 and z equals to a third are the poles of the function f of z. So remember, this integration is carried within a circle of radius 1 unit. So if you draw the unit circle, so this is the imaginary axis, this is the real axis, real axis. So if we call this one z1, this one z2, so you see this would be -1, this +1, negative I, positive I. So a third would be somewhere here. And then this is where I have z1. So this outside. So we don't care about this. So we concentrate on this one that is within the unit circle. So residue at z equals to a third will be given by limit as z approaches a third of z minus a third times f of z. This by definition. So which will give us limit as z approaches 1/3 z minus a third. F of z is given by, from this point, it is 1/3 z squared minus 10z plus 3, which can be factored as z minus 3, 3z minus 1. So I have limit z approaches a third, z minus a third, and then times 1/z minus 3, and then 3z minus 1. Limit z approaches a third, z minus 1/3, and we say this can be written as 1/z minus 3, and then I can factor out a third. I can factor out here 3, and then so I'll have to write this one as z minus a third. So then this cancels out, and we'll have limit z approaches a third of 1/3 into z minus 3, which will be 1/3 into a third minus 3. So a third minus 3 times 3, that is minus So head, so just a minute. So we'll have minus 1/8. So which means hence by Cauchy residue theorem, I integral is given by 2 pi I sum of residues within unit circle C, and because only this pole of 1/3 was within the circle, so this other one is not part of the solution. So I'll have I is given by 2 pi I times minus 1/8, which will give us minus pi I over 4. But then we were to calculate the value of this. So the value of the integral here along C of 2 are actually the original integral. So I can just say the original integral was given by this star equation. This was the integral from 0 to 2 pi d theta over 5 minus 3 cosine of theta. So then, because we have the value of this integral, we simply need to multiply minus 2 over I times the value of this integral, whose value we have found to be minus pi I over 4. So we have times minus pi I over 4. So 2, 1, here 2, I and I, negative and negative. So we get pi over 2 as the answer. So therefore, the solution to the problem, therefore, the integral from 0 to 2 pi of the theta over 5 minus 3 cosine of theta is given by pi over 2. So that's how we solve that problem. Thank you.